Good morning, Hasan. Today we are diving into a fundamental concept in linear algebra, the basis of a vector space. This idea is crucial for truly understanding how vector spaces are structured.
Good morning, Dr. Akira. I've been looking forward to this. I have the definition here, but I'm eager to grasp the intuition behind it, especially the proofs.
Excellent. Let's start with the definition of a basis. So, definition 1 states, let V be a vector space over a field F, and V1, V2, and so on up to Vn be vectors in V. The set of vectors V1, V2, Vn is said to be a basis of V if it satisfies the following two conditions.
Right. The first condition is that V1, V2, Vn generate V. This means V is spanned by these vectors. So any vector in V can be written as a linear combination of these basis vectors.
Precisely. And the second condition?
The second is that V1, V2, Vn are linearly independent. This means no vector in the set can be expressed as a linear combination of the others.
Perfect. In short, a basis is a set of linearly independent vectors that span the entire vector space. This also implies that every vector in V can be uniquely expressed as a linear combination of the basis vectors. This uniqueness is a direct consequence of linear independence.
That makes sense. It's like they are the minimal set of building blocks for the vector space.
Exactly. Now, this leads us to Theorem 1, which is quite powerful. A finitely generated vector space has a basis. This means if a vector space can be generated by a finite set of vectors, then it must have a basis. We'll prove this soon.
So, every vector space that isn't infinitely huge in its generation is guaranteed to have a basis?
That's a great question, Hasan. For the purpose of this video, the proof we are about to explore, we will focus on finitely generated vector spaces. The existence of a basis for all vector spaces, even those that are not finitely generated, is a deeper topic that requires more advanced tools. But for now, let's stick to this foundation. It's important to note that, in general, a basis of a vector space, if it exists, is not unique. There can be many different bases for the same vector space.
That's an interesting point. So while the building blocks might change, the idea of a minimal spanning set remains.
That's right. To prove Theorem 1, that a finitely generated vector space has a basis, we first need a crucial tool, this lemma, the basis extension principle. Lemma 2 states, let V1, V2, Vk be linearly independent vectors. If they don't generate V, then if we take an arbitrary vector W in V, such that W does not belong to the subspace spanned by these vectors, then V1, V2, Vk, and W are linearly independent.
So, if I have a linearly independent set that doesn't span the whole space, I can always add a vector from outside its span, and that new set will still be linearly independent?
Exactly. Let's look at the proof. Since W does not belong to the subspace spanned by these vectors, W cannot be expressed as a linear combination of these vectors. This directly implies that V1, V2, Vk, and W are linearly independent.
That's surprisingly straightforward. If W could be written as a combination of the others, it would be in their span. That contradicts our assumption.
Precisely. Now, with this lemma in hand, we can prove Theorem 3, which in turn proves Theorem 1. Theorem 3 states, let V be a finitely generated vector space if V1, V2, and so on up to Vr generate V, then we can choose some vi1, vi2, and so on vin from v1, v2 up to vr, where I1, I2 up to in are in the increasing order, so that these vectors is a basis of V.
So, if I start with any set of vectors that spans the space, I can always pick a subset of them that forms a basis. That sounds like a way to trim down a spanning set.
That's an excellent way to think about it. Let's go through the proof step by step. First, let G be the set of these vectors v1, v2 up to vr. So we call it the initial set of generators. First, a trivial case. If all vectors in G are the zero vector, then V consists only of the zero vector. In this case, the empty set, or sometimes the set consisting of the zero vector, by convention, depending on the definition, is considered a basis. And we are done.
Makes sense? The zero vector space.
Next, suppose G contains non-zero vectors. Take the least index I such that Vi is not the zero vector. Let I1 be I. Then we set the set B as the set consisting only of this vector Vi1. This set B is linearly independent. If the entire vector space V is spanned by this set B, then B is a basis of V, and we are done. If V is not spanned by the set B, we go to step 2.
So we start with the first non-zero vector and see if it spans the whole space. Probably not, usually.
Exactly. So, if V is not spanned by B, we move to step 2. Let I2, which is greater than I1, be the least index such that Vi2 does not belong to the subspace spanned by B. Such an index I2 must exist because all remaining Vi's were in the subspace spanned by B, then V must be equal to the subspace spanned by B, which contradicts our assumption that V is not equal to the subspace spanned by B. Redefine B as this. So we add Vi2 to B. By the basis extension principle, that's Lemma 2, the new set B is linearly independent. If V is equal to the subspace spanned by B, then B is a basis of V, and we are done. If V is not equal to the subspace spanned by B, we go to step 3 and repeat this process over and over.
We are essentially adding vectors one by one, ensuring they are linearly independent from the ones we've already picked until we span the whole space.
Precisely. This process stops at, say, step n, which is less than r, as V is finitely generated. Then the set B, consisting of Vi1, Vi2, and so on up to Vin, is a basis of V. By this theorem, we have also proved the existence of a basis.
So, we are guaranteed to find a basis within the original generating set. That's brilliant. And this also proves Theorem 1, the existence of a basis, since we started with a finitely generated space.
Exactly. This theorem is a constructive proof for the existence of a basis. So, how do you feel about the concept of a basis now?
Much clearer, Dr. Akira. Understanding the definition and the proof of its existence makes it feel much more concrete. It's fascinating how these fundamental ideas build upon each other.
That's the beauty of mathematics, Hasan. While we've seen a basis isn't unique, the number of vectors in any basis for a given space is unique. We'll delve into that fascinating concept, the dimension of a vector space, in our next session. For now, keep practicing and these concepts will become second nature.
I will. Thank you, Dr. Akira.
You're most welcome, Hasan. See you next time. Thanks for watching. If you have any questions or comments, please write it down in the comment section below. And if you like this video, please hit the like button and don't forget to subscribe to this channel. See you in the next video. Bye.